So then, the problem, the next step in the puzzle is, so if you really want the pi calculus to be a fundamental theory of computing, and you sneak in this set that has this structure, then, you have to worry that the set, doesn't kind of sneak in a notion of computing on, already baked. So like, if the pi calculus is like gonna like be the birth of your notion of computation, there's no other notion of computation it imports. And if you import a notion of computation through the set of names, you haven't really accomplished your goal.
Yeah, sure.
Right. So that's right. So basically, then the row calculus is the only way to achieve that goal. You just simply say, well, let's just make the set of names somehow be the set of processes. And that's where the idea of quoting processes as names comes about. And then the algebra on processes becomes an algebra on names.
Wow.
And so it's, it's like basically the smallest thing that can achieve what the pi calculus set out to achieve. And then it turns out that, nu is just syntactic sugar. And then the other thing that it solves is, people were wondering about, well, what about higher order processes? How do we do that? And so there's this thing called, the higher order pi calculus. And in order to get higher order phenomena, it turns out to be really complicated, but then you can show that you can compile the higher order stuff down to the pi calculus. So what's really going on? And it turns out the row calculus gives you all the higher order phenomena. And it gives it in a way that's like basically lines up with what we know in the internet. You ship code around, right? You ship code from one place to another. And then when you receive the code, you can start running it. And that's the whole idea of, you ship quoted processes. And when you get a quoted process, one of the things you could do is start running it. It's a totally natural, it fits with our experience and our intuitions about this kind of stuff. So
cool. Thanks for the overview.
Yeah.
Should we set off?
Yeah, let's get rocking.
Cool. I can start with an update. Cool. So last week, Vlad was talking a lot about the tree operation stuff. So we have this binary tree of shards, and he thinks it's like somehow much better if we have this load balancing thing. So I spent some time thinking about like how we can kind of have that. I was thinking about it last week, kind of bled into the start of this week. But essentially at the last stand up, I said something like each shard can have at most one set of master shards, and where these master shards have to essentially move together. But I think we can actually relax it. This was like the big realization of the week, to just saying that each shard has a single set of master shards per block. Can't put this away. That's pretty understandable, which is that each block defines the master shard set for its children. So essentially, this is exactly like validator set rotation, where like a shard can kind of switch where its master is just by in its block. It specifies which shard its children are under, and then we might have to add some conditions like no cycles or something, because then things get weird. But other than that, it seems like it works pretty well as far as like maintaining the fork choice atomicity stuff goes.
Sounds like a DAG.
Yeah. It is even in the tree structure.
But sorry, that was a bad joke.
It's an evolving DAG.
Yeah, it was just pretty interesting to see that like the same strategy for validator set rotation kind of works here as well. It's like a interesting way of doing things, I guess.
Mm-hmm. Yeah.
And then so that was one effort. And other than that, the only other thing I did this week was like what I'm calling the great education effort of 2018. So pretty much just trying to get like lots of resources and materials around CBC Casper up to snuff. So as of now, if you're interested in checking out the wiki and giving feedback, that'd be awesome. Let's direct it to anyone who's interested. But we have like an explain like on5, some good progress in the FAQ, and a resource list, which is cool. So yeah, that's it for me.
What's the URL for that?
If you go to the CBC Casper wiki, I'll post it right now. But it's on the research Python code base thing. I'm posting it now. There you go.
Thank you.
First. Thanks.
Michael Birch, you want to go?
Sure. I don't have much in the way of Casper to talk about. Kent and I were working on fleshing out more of the R chain state and how it looks on the blockchain, and sort of spinning up, getting ready to implement proof of stake in Roland, basically.
Sweet.
But I think Kent actually has some Casper / sharding related stuff to talk about based on discussions he was having with Nash, which I didn't get a chance to read before I started here because there's a lot of it, but maybe Kent can elaborate on some of that.
Yeah, Kent, go. Oh, that's weird. That'd have to be Christian. Can you unmute Kent? There we go.
Thanks. Yeah, I don't know why that happens, but yeah, so okay. I guess one thing I want to discuss here is what Nash and I discussed on Friday. And Nash brought up this interesting point that you don't have to randomize validators or have a smallest validator set size, as long as you keep track of, I guess, what's in a block. And before, I guess, you jump on me about, I guess, issues about, I guess, potential censorship and whatnot, I guess I just want to make it clear that this is just like one trade-off, right? And like if you think about it, there were, I guess, a number of combined issues that could happen. And so I just want first, if you have too small of a validator set size, then you're prone to DOS attacks. I guess there's two forms of this. The first is that, you could have someone with a large stake come in and just stall on your shard. Or, you could bribe someone on that shard to just stall themselves. And as a result, stall the whole shard. And so these two things are, they're an issue. But if you think about it, the validator sets can be controlled by policy. So, so basically, you can have a policy that says, I'm the only validator in this shard. And that would mean that, no one can swap out with you. That means, you won't have to be worried about someone with a larger stake coming in and taking over your shard. And since we're assuming that any higher shard can take over your fork choice, this sort of assumes that there's no malicious higher shards. But I think that's an okay assumption given that they're higher shards for a reason. And so, there's no, that's the assumption.
That seems like a really weak assumption, to be honest. Like you can have cartels, right? That's kind of the whole point.
Well, so
in fact, you can imagine an evil cartel, forms a bunch of lower shards, each of which are dominated by a tyrant from the cartel. This seems like a totally, possible outcome in the world.
Well, but I guess what I want to say is that what we currently have, although that's sort of all over the place too, is I don't think it resolves that, right? Like, if you have enough stake to attack the root shard, then you have the same problem.
Yeah, but having enough stake to attack the root shard is a little different than what we're talking about. The risk at the leaf was that people can kind of eat from the bottom, which is a lot easier than eating from the top.
Are you saying that you can eat from sort of like the middle, if that makes sense? Because if you eat from, so remember that the leaves can have a policy that says you can't swap out with me, right?
Who puts the policy in place?
The person who creates the shard itself. And so the policy can be different across leaves. So why are we? I mean, that's under an assumption that it's not the protocol that creates the policy. I mean, that creates the shard, right? That's a different model. Well, so I guess to back off a bit, I'm imagining what you can do is you can submit to the top shard, or I'll call it the root shard, sorry, that the sort of policy that you want to implement in your newly created shard, and then the top shard the root shard will allow you to create it, and it will set you as the first validator, for example.
Yeah, isn't that like very explicitly not Casper though? Like that's very explicitly not how this protocol has worked. It's been a while since I've showed up. Sorry to jump in and say that, but I feel like that's like definitely a different protocol.
But more importantly, it's kind of the tail wagging the dog, right? The whole point of the contract decoration with the name groups or namespaces is that you figure out what shards you need, and then you enlist because you have a contract that needs to be deployed. Right now you've got it. It's like it's not driven by the input of the contracts; it's driven by some validators, right? And now they're completely incentivized to organize themselves in cartels in whatever way they want, and so they decide. So a cartel comes together and decides they want to have this particular policy, right? And how does a higher level shard know that this is a cartel? They don't.
Yeah. So I mean, first of all, I agree with Rick that it's not Casper. I mean, if that, I guess, puts this off topic, but I mean, I'm just saying it sounds like a way to achieve what Greg sort of originally wanted with, allowing this whatever model to have different, or I guess, it's sort of, it allows, the neat things like if this shard wants to focus on storage, maybe then it can do that. Like it can have a bunch of validators that, have a lot of disk space, but maybe not so much compute. And that kind of, you can have those properties, so to speak. I don't think that the cartels I guess I don't see the concern there because like this is already under the assumption that you're taking a risk if you're going into an unknown shard, right? If you're putting your tokens into a shard with a
Why?
Well, because the validators can stall, right? Because as Greg just said, you can form a cartel and create a new shard. Then if you can convince someone to move your tokens there, then you can just stall on that shard. And
so I think like maybe this is like a liveness consideration or like a censorship attack or something, but I think that Vlad would probably push back by saying that this is like the incentivization layer, right? Like we can just say, if all our shards are progressing except your shards that you're on, and for some reason we don't have blocks being made there, then we're gonna punish you, and we're gonna punish the people. We're gonna punish everyone responsible for this, right? So it's like, yeah, they can do it, and we can also do our best to make it unprofitable. And then there's also the point that like if validators can kind of choose what shards are going on, then somehow maybe censorship attacks are worse, or even just attacks in worse are general because validators have more choice and more options, really.
Yeah. I mean, I feel like in this community, part of the reason I come here so frequently is I'm busy in a lot of other places. But one of the benefits of these protocol discussions is it is the model where validators don't get to decide where they're validating, and then you have a lot of benefits that emerge out of that. So, I mean, I don't think we have any issue with heterogeneous validators. If the consensus algorithm is deciding how those resources are allocated, right? I mean, maybe your storage is in a different shard than your, the percentage of your CPU, right? I mean, that's entirely possible, and probably, and almost probable in certain circumstances, depending on how storage and compute are modeled. So I don't think that you need to sacrifice the consensus algorithm selecting the validators to create a heterogeneous pool of validators.
So I want to support the idea that there is a notion of service level agreement that can be associated with a shard. I think that's a reasonable thing. The question is whether or not it's set by the validators or set by the protocol. So in particular, if it's tilted in a user-centric way, so there are contracts that need to be deployed, and those contracts have requirements with respect to their deployment in terms of the names that are being served, and those names as communication channels have certain kinds of requirements. Then the protocol can be in charge because the protocol is now justified. We have these 100 or so contracts that all have these kinds of requirements, and then they basically take validators that have certain listed characteristics and set up a shard. That is much more cartel busting than if you have the validators have the choice. I think that's the trade-off I was arguing.
Yeah, that second, your model, of course, I mean, makes perfect sense to me. And I don't see, I mean, especially if the resource requirements are determined under consensus. I mean, this is something we were talking about years ago where you provide, it's crazy to say that, but where you provide the source to the validators evaluate the source code, and then they figure out how to distribute those resources. Yeah.
But Kate, you were about to say something.
Yeah. So I guess my response to Rick is that, allowing the protocol based on resources to sort of do this heterogeneous sharding is sort of like against randomization, right? So like, I mean, you can still have randomization, but it's sort of offset by how much the protocol values your resources, right? Because then you can start building cartels that say, okay, we're just going to focus on storage. And so let's get on all these storage shards.
Sure. So there's a big difference between non-determinism and random, right? And we're not really striving for pure randomness in general. We're striving for an adversary's inability to predict exactly where they will be without being, 51% of the nodes, generally speaking. Although in Casper we relax that 51%.
Mm-hmm. Yeah. So I guess I agree. Like if you do enough, I guess, randomization and if you ensure that your shards are like large enough, then I think it's fine. Like but I guess I was just saying that this alternative model that Nash was pushing for, it does scale better in some sense. Like it's less resistant to the censorship attack, just as Nate said. But it first of all, you wouldn't have to have in Vlad's model currently, you have to be on the leaves and then all the way up to the root, and that's fine because but you can't be on a leaf and not on a higher shard. And this is because you would then not be in sort of in control of your own fork choice. But if you think about it, you can imagine it as you have 0 weight on your higher shards, and it's fine as long as you trust whoever is actually on those higher shards, if that makes sense. And I don't know, it seems like it's just.
I don't understand. What's the scaling characteristic that you think is better?
The fact that you can choose your own, I guess, shard, and that you can choose to be exactly where you want to be. And I guess it's like you always have, I guess, less overall security, if you think about it, but on each shard you could have more security.
Sorry to jump in, but I think you just used the word "you" to refer to two different groups in like the same paragraph. So if I'm an application developer, when I write my source code, the requirements of my code determine where my contract is executed. And then as a user, I can choose to interact with that contract or not. And then presumably in some further version of the protocol, we can imagine that the consensus algorithm will be intelligent enough to load balance and put validators and users in relative close network proximity, right? But in your description, you just talked about, I think, and I'm not sure, I think you talked about users, application developers, and validators all as you. So I think that that's where my confusion is coming from. I think what you're proposing is a little too biased towards validators, at the cost of the users. And I have to go very shortly, but
I think it's not surprising that comes from Nash.
Yeah, I mean it's biased to the contract writers, I guess, and the validators. I agree.
No, it's not biased to the contract writers. That's exactly the point. Because the contract writers are submitting these things, and we're now just letting the validators form the cartels. And again, we still don't know if at the end of the day, after they've self-assembled, if we can deploy a contract. They decided where they wanted to go. They all went where they wanted to go, and now we've got this contract, and there is no shard that supports the name groups that we have calculated from the contract are necessary.
Well, so the name groups, or I'm just going to call them things that, decide where the contract goes, can be controlled in this model by the contract writer, right? Like the contract writer can say, I want to submit this contract to shard X. And the way they would do that is annotate that by the name group X, right?
Yeah, that makes no sense to me at all, right? Because we want the whole idea was to put a firewall between the name groups and the actual topology of the network. We really, really don't want contract writers writing to specific network topologies. We want contract writers writing to abstract declarations of the requirements to run their contract, and then have the network self-assemble to make sure that it supports those requirements, rather than, because that would make it really, really subject to attack, right?
You're talking about the censorship attack, right?
Not just censorship attack. I mean, there's all kinds of economic security problems with that model.
Or like are you saying like you're offloading that sort of?
I mean, like for the last decision. 20 years, for the last 20 years, people have been deploying internet applications, knowing that they should never, write inside their code assumptions about the topology of the network, because they want their application to be deployed on lots of different kinds of networks. So if they abstract the network topology from their code, then their code gets a lot more reuse, especially because the network topology is constantly evolving. Right? We want the network topology to be evolving, and we want to be able to find a wide range of network topologies that satisfy the contract or the program requirements.
I see.
Yeah, I mean that's just like best practices for the last 20 years, I think.
No, I definitely agree that it puts more strain on the contract developer, which they're not there as sort of network specialists, and so exactly. I do understand that point. Okay. I think I'll stop right here on pushing this, but I just wanted to throw this out there that this is a model, and there is a scalability gain in my opinion, but yeah, that's it.
Cool. But I actually really appreciate this dialogue, because what the dialogue helped was to clarify a particular set of trade-offs, right? And what it really comes down to is a trade-off on the validators versus the contract writers, right? And I really, I think we need to, because the contract writers have so many, because the validators have so many other levers, and the contract writers, by design, need to have, much less visibility into the overall network. We need to give them as much leverage as possible. Right? They're essentially going blind. They're deploying it against a computer that's constantly reconfiguring itself. So they need to be able to say something about the requirements of the computer that configures itself. Anyway, but I thought that was a really intriguing conversation. It really brought to light a lot of issues. So thank you.
Cool.
I'm working on at the other end of the spectrum. I've been in addition to working out the whole name group architecture with folks. I have largely been looking at the axiomatization of consensus, returning back to this this idea. I have a little video that I want to put in the chat that goes all the way back to some comments I made to Vitalik and Vlad a long time ago. let's see if I can find it. Here it is. Okay, so here's a little video that people can watch at their at their own leisure. Basically, what they I'll cut to the chase. Give people the punchline there. So there's what they explore is, suppose you take 3 points in the plane, and then you pick a random point anywhere in the plane at all, and the rules are you assign some distribution with respect to you're going to make a random choice, and so like pick a random number, and based upon how that number lies with respect to this distribution over the first 3 points that you picked, you're going to move halfway towards one of the points. So imagine, so to get a geometric intuition, imagine the 3 points form a triangle, and you've got a dice or a die, and 1, 2 is the numbers 1 and 2 go to one of the points, the numbers 3 and 4 go to another one of the points, and the numbers 5 and 6 go to another one of the points. So you random numbers rolling a die, right? And then like if the die lands on a 1, then the starting point that you picked, this random point that you picked, you move halfway towards the first point, right? And then from there, if you roll a 5, then you move halfway towards the third point, and so on. And if you keep iterating this process, what happens is you draw the Sierpinski gasket. And what's this got to do with consensus? Well, think of each of the different points in the triangle as a block proposal, right? So these are all 3 competing block proposals, and then the random numbers are effectively bids. So you have some starting initial bid with respect to those proposals. So this is like essentially now the distribution with respect to the stake, all right? And as the bid, as the sort of stake sloshes around, what happens is, so as you imagine that you're sending a bunch of messages around, and those messages roll up to a particular distribution of the stake. Then as you do that, as you iterate this message passing, what you end up with is drawing the Sierpinski gasket. So that's the basic idea. And you can relate, sort of the regions that don't get visited. Anyway, there's a fixed point to this iterative function system, which is just the passing of messages that go round and round and round, trying to reach consensus, right? And of course, it's through FLP impossibilities, it could be that the point never converges. And so, the question is, what can you do to tip it towards convergence? So then, hopefully that geometric intuition is very clear. So then it turns out that the fixed point here, which is the whole Sierpinski gasket, the operator that picks out that the calculation. So there's a, how do I say this? There's always going to be a fixed point operator that picks out one of these kinds of fractal-like shapes. That operator is called a fixed point operator, and the fixed point operator is correlated to the trace that I've been talking about in these trace monoidal categories. And the trace, when you use the trace around the composition of 2 of these systems like that, is what forces the two systems to agree on each other. So I'm just walking through some of the history of, how we got to the trace monoidal construction just from a set of geometric intuitions. Let me stop there and make sure that makes sense.
Thanks, Greg, for pausing here. I was actually just going to ask you to do that. Talking about the Sierpinski gasket example, I just want to try to phrase back to you what you said just to make sure that I understood it correctly.
Yeah, sure.
So you said that each of the 3 points of our initial triangle represents 3 block proposals, and our moving point represents the current status of our consensus, right? And the closer we are to any of the corners, the closer that block is to being accepted. Is that?
Yeah, that's exactly it. Yeah, that's right.
Okay, cool. So now the part that I'm having trouble relating is the local the local phenomenon to the global phenomenon, right? So the local thing is I've got this point that's hopping around this triangle, trying to get closer to one of the vertices. But then if you zoom out and look at the global picture, the pattern that the point traces out is this really interesting fractal pattern. And so I'm not quite sure what the global structure has to do with the local point ever reaching one of the vertices.
Oh, no. FLP impossibility says that, it's quite possible that it won't ever reach one of the vertices. And you can't avoid that.
Yeah, sure. So I guess I don't really understand what the point of noticing the global structure is in this context. Oh,
yeah. So the point of noticing the global structure is to understand, if you didn't know that the global structure was there, you just start looking at you might think that it's just a random path, but in fact it isn't a random path. And what you really do have is a fixed point operator happening in this in the whole system. So there's an algebra here that we can exploit, and the algebra and so the next step is once you recognize you have this fixed point operator, then you recognize that you have this trace. And
but let's before we keep going to the trace section, I'm still not quite seeing the reason for making this jump, because what I care about when we're talking about consensus is where the point ends up eventually. I don't necessarily care about its entire history, right?
Actually, no, that's not true.
Okay.
And the reason you care about this is because these systems are never single. These systems are always composite. That's the whole idea is that once you get the compositional structure right, so it's never just one block proposal. It's this block proposal is depending upon that block proposal, which is part of a chain of dependencies, and which is actually part of a DAG of dependencies, right? So we're looking for the composite structure, and it turns out that when you have a handle on the composite structure, then you can go back to the local structure and learn more stuff.
Okay, so I think I think I've lost the analogy then a little bit again. So the initial idea was that each vertex on the triangle was a proposal, and we were trying to figure out which proposal to go with. But now it sounds like you're talking about every point that we make is a new proposal itself, and we're trying.
No, all I'm saying is that off of any one of the points on the triangle is another triangle or another polygon, right? So really, off of any of the vertices, you span outward with all these different polygons.
You never reach any of those vertices until So yeah,
It's not-
there's something
don't-
after any given vertex. Like there's things happening afterwards, but I'm still having trouble relating that to our little dot that we're following around the Sierpinski gasket.
So again, how do I say this? It's not about not reaching, but the thing that you reach is the fixed point, right? The fixed point is the gasket. Don't worry about the individual point yet, okay? Because it's not just about the individual point. In fact, it's there are going to be multiple points or clusters of points that have to do with the fact that we're always looking at different. You can decompose the state space, right? And then and they're moving around in a larger structure. And then on top of that, you have sequential. So that's the parallel composition or the concurrent composition. And then on top of that, you have sequential composition, which is once you, if you reach a decision point for some piece of the state, then it forks off, or it branches off into another geometric shape, which is impinging on the vertex. Is this making sense? Do you understand what I'm saying? So I'm not interested initially in just the initial point. What I'm interested in is showing that the structure of the paths of the initial point there's an underlying algebraic structure, and when I see the underlying algebraic structure, then I can exploit that to influence how selection amongst the paths. That's the core idea, that the paths are not random. They lie inside a very, very rigid structure, right? Which is this fractal shape, and that rigid that fractal shape has an internal compositional structure. And I can use that compositional structure to select amongst paths. That's the key idea.
And paths here are representing sequences of messages that are trying to get to consensus.
Correct. That's
okay.
Right.
So there's a structure on the sequence of messages, and you would like to, by knowing something about that structure, influence the consensus, or the sequence as a whole, like where the path ultimately ends up.
That's correct.
Okay,
That's exactly.
Gotcha.
Yes.
So once we recognize this, now you're saying that there's a trace on.
Right. So in point of fact, a fixed point operator always corresponds to a trace. That's a theorem.
Could you elaborate on that a little bit more? So when I hear trace, this might be my lack of higher mathematics showing beyond sort of what's relevant to physics. When I hear trace, I think about like the trace of a matrix or the trace of a linear operator.
Yeah, and they're closely related. It turns out that they're closely related. Hang on a second. I need to grab a document and I can show you the theorem. Okay, so just grab, oops. Okay, so just grabbing this document off the interwebs here. Hang on a second.
I know we talked a lot today, but I do have, I guess, something to a document to show, I guess, that I was writing before I got excited by Nash's proposal. Let's put it that way.
Cool.
Yay.
Sweet. Would love to see that as well. Hang on, I'm almost there. Sorry, just grabbing the. So there's the traced, there's the tortile. Oh yeah, sorry. And there we go. There's the fixed point. Okay, the trace fixed point correspondence. So let me just bring this up. Okay. So go here and then do a screen share. Okay, so it turns out that you can kind of characterize that fixed point operator in a categorical way, more or less as a family of functions that take you from a product. So it's the morphisms that take you from a product with X and X over into getting rid of the X. So this extra X here is where you feed stuff back in, right? So you think about a morphism that runs from A to X, and you just expand it with an extra X, so you can kind of loop on the X until you're done. Is the basic idea. And then it turns out that we have this a theorem which says that you get this correspondence between these fixed point operators and the notion of a trace. Now, the notion of a trace, which was the part that was providing a little bit source of confusion, is characterized here. So effectively, if you've got morphisms that look like this, right? So they've got an input and an output of A, but then they also have this extra wire, which is an input of X and an output of X. Then the trace basically provides a loop back. So you could think of the flow of operation as kind of very typical accumulator style computations, right? So I got an A. I look at the shape of the A. If it's like my base case, I do a simple calculation and I emit a B. If it's not my base case, then I need to loop. So I go and I recurse down the structure of A because I've got some kind of transformation from A to B. Let's see, someone is chatting.
Sorry. Please.
Yeah, no worries. Okay, so I've got some transformation from A to X, and then I can loop on the X and check the recursive case. Am I done? If I am, I can emit a B. If I'm not done, I can loop again. So this is the sort of that's what's going on here in the trace. It takes something like this to something like this, where you essentially you hide away the recursive part, and then there are some laws that I won't go into all the laws, but
sure, they're just to make this thing well behaved so that it does what we think it should do.
Exactly right. So it turns out that this kind of looping behavior is, another way of characterizing the fixed point behavior. Big surprise, right? this nothing really surprising in this at all. And so once you understand that, then the other piece of the puzzle that gets to be interesting is the traced composition. And the reason that, so here's effectively the traced composition. So you've got your morphisms that they're a little bit funny because they have an A part and a B part, and then let's see if I can explain this. So an arrow is going to be from pairs. So every object has to have a plus side and a minus side, right? Which you could think of as effectively input and output. Typically, the way this is drawn is they reverse the polarity of the target and the source. Hasegawa in this paper keeps them the same, and then puts a twist somewhere else in the diagram. But effectively, what you do is it's mutual feedback. So if you're composing F and G, that means so F runs from A to B, and B runs from B to C. But remember, the A's and the B's are effectively doubled. You've got input and output on both sides, right? So so when you come in on an A, right, if you're done, then you can go out on a B, and if you're done, you can go out on a C. Suppose you're not done, right? Then you may loop around, like, if you come in on a B, you may not be done, in which case you have to loop around on the whole thing. Otherwise, if you are done, then you can come out on the A minus, right? So it's a kind of mutual feedback is what it is. There's a better picture that I'm more familiar with than the way Hasegawa draws it in a slightly different way. There's a better picture that I've gone over in these kinds of settings, but effectively what it is it's mutual feedback between the two morphisms. Now what are these morphisms in the blockchain? These morphisms are effectively little Casper processes, right? They're so think of it as like the smallest possible contract and the smallest possible contract that have some kind of dependency on each other, right? So they have and the only place where they actually have to agree is on the mutual state, right? So in our geometric example, the place where they would have to agree is, I've got to be able to fit one of these. I got to be able to figure out on which vertice I take these two fractals and glue them, right? So they have to agree on which vertex we're going to glue the two fractals together. So that's the other way of thinking about how this fits together. So
Greg, is this also relevant to the sharding discussion, because the idea is that there's a mini Casper running on every shard?
It's not really a mini Casper running on every shard.
Well, sure, it's a full blown proper Casper, but if we're thinking about the blockchain as a whole versus like zooming in on a shard, there's
exactly. So yes, and the short answer is yes. The point is, when you get the compositional structure correct, the sharding structure just falls out.
That makes sense. There's a canonical sharding structure.
Yeah, exactly. Or a range of canonical sharding structures. That's the idea. Anyway, I've talked forever. I apologize, but anyway, that's what I've been working on. So there's a set of theorems that all fit together in this particular way. So and I'm just working out how all the theorems fit together. So I'll just zoom out. I gave a history of the intuitions that led here, and then the main set of theorems that I'm working out is, because of FLP impossibility, we can't live in these sort of really nice traced monoidal categories like partially injective functions, sets and partially injective functions. And the reason is because the trace always exists, which means the fixed point always converges. But we know with FLP impossibility that that's not the case. So we have to live in order to have this trace monoidal account be faithful to the situation we're modeling. We have to have what's called a partial trace. So I'm piecing together, and the partial, so basically what we say is the trace doesn't always exist, but when it exists, it obeys the nice rules around trace composition. And so it turns out there are a bunch of representation theorems here that I'm piecing together to try to make sure that I can get a path from the trace monoidal axiomatization out to the row calculus. So we have this nice partial. We have an axiomatization in terms of partial trace that sort of succinctly captures just what we need in order to have this feedback mechanism that's forcing agreement when it exists, right? And then mapping from that onto an implementation that looks like row calculus. So that's what I've been doing, and I'm doing that in preparation because we're going to go meet with a bunch of researchers who know this stuff really well, but have never thought about how this might apply to consensus. So I'm putting all our ducks in a row so we can have, those a bunch of researchers at Oxford, pound on us and say, "Oh, you got it wrong here. You got it wrong here," and help make sure that this line of research has sanity, at least from their perspective.
Awesome. Well, that's super cool. I appreciate you taking the time to answer all of my questions and make sure that I'm following along with.
No, I really appreciate the level of engagement. But I'm late for the dev stand-up, so I better jump over there.
Yep. Sounds good.
Thanks, guys.
See you there.
See you there. Ciao, ciao.
Bye.